Okay. Hey everybody, welcome. We're going to get started because I don't want to keep you here any longer than you need to be. Hold on, but you're very loud. Thank you. I'm going to turn it up. That's better. But thank you for being here. We have a few guests, believe it or not, and we are recording this, posted on our website for graduate projects. So thank you everybody for being here. My name is Chris Kaler and I'm the graduate projects coordinator. So my job is to make sure that all the projects are functioning and have what they need, but also supporting the faculty advisors as they do their work with the students that they have on their teams. So, but I also help with the actual facilitation of our lectures and things like that we do once a week. So tonight we're going to do a brief overview of the course. It's a two-part course, and you'll hear more about that here in a second. We're going to do some project overviews and then answer any questions that you might have. So just play along with this if you've already answered them. How many of you are getting your master's degrees? How many of you think you're going to go on to PhD? Okay. How many of you are at CU right now? This is kind of a silly question. But anybody not from Colorado? Raise your hand if you're not from Colorado. You came here outside of the state. How many of you know your focus area? Okay. Okay, one person doesn't know. That's good. Nathan, you know you're graduating.
I raised my hand.
Oh, okay. And do you know why you're here? This is kind of a silly question. You're here for the cookies, or you're here to potentially do this course next spring or next fall. And then you know what you're going to do after you graduate. Get a job, do research. Anybody not know? Okay. I have a reason for asking all that because I think the graduate projects program is a great way to get to really dabble in your focus area or to help figure out what you want to do when you graduate and gives you a chance to kind of explore that. So if you're in a Master's of Science degree here at CU, or at least in the Aerospace department, you can get that master's degree through 3 different methods, primarily 3. You can write a thesis. Who's doing that? Anyone? Okay. You can also take graduate projects, or you can take additional coursework and either get a certificate or just the coursework credits. So graduate projects is a way to get your master's degree. It's also open to all graduate students, even if you're not looking to do it as your method of getting the degree. And we try to expose the students in the course through hands-on activities or project-related work in project management, systems engineering, but also hopefully a real-world project that has different aspects of an aerospace engineering project. So you'll be working on a team if you do this. That team may be 12 students, it may be 2 students, but you're connected to a bigger group too. So, and then the breakup of the course is that we have, there's a once a week lecture, and we meet in all together, all the projects. We have a lecture. Right now it's Mondays from 4:10 to 5. And then all of the different sections have their own meeting times where they meet with themselves and their faculty advisor. And we have 4 sections of projects, and you're going to hear about those tonight. The overall lecture class, which is once a week, there's weekly lectures, there's timesheets, you give updates to the entire community of project students. There is a book that you have to read for each of the different sections, or not sections, but whether it's 5,018 or 6,028. And then there are project collaboration opportunities within the lecture time. And then if you're in your project, the students that are here that are going to talk to you tonight can talk about that. But you have bi-weekly lab section meetings, you have group work, breakout meetings, plenty of reviews and meetings with your customers. You have peer evaluations, which you all just did, documentation, as well as just the project and teamwork experience. So the objectives of this course, before we get into having some of these students present, is again, you get some project management systems engineering experience. Maybe the students presenting tonight can say if that's happening or not. I've seen some great examples of both of those happening right now this semester. You do formal presentations, not just to me and your peers, but your customer, your sponsor. And that presentation is based on your work, which is really the heart of what Graduate Projects is about. You get to hopefully build something, test something, verify something, or some combination of that. You get to work on a team. And configuration management, that's really a big selling point, isn't it? No, it is part of the job. How many of you are doing some aspect of that? Yes. Trying to with GitLab. Not so easy. Yeah. You will learn about career opportunities both in academia and industry, and then you get perspectives from alums as well as experts working in the field. So that's all of the objectives of this course. And the projects sort of blend all these together as you're doing them, both the lecture and the project. So tonight we're going to do this brief introduction. I'm going to have Nathan come up, and I have a video also from a former graduate student in these programs. And then each of these teams are going to do a 5-minute presentation, which I must admit, some of you submitted a lot of slides for 5 minutes. So it's okay to skip some of them so that we're not here till 8 o'clock. Okay. And then there'll be time for questions. So here is one student that took the Graduate Projects course program a couple years ago. So we'll watch this.
My name is James Mason, and I am a research scientist and engineer at Johns Hopkins Applied Physics Lab, working on and leading NASA missions. I was a student in grad projects in the 2011 to 12 academic year. And then I just stuck with that project, and it became about half of what my PhD thesis was based on. We were working on a CubeSat that ultimately NASA funded. Grad projects is where I discovered the career path I wanted to be in. We launched that CubeSat called NICS from the space station just a week after I defended my PhD. On the actual spacecraft itself, I had laser engraved everyone's names who had worked on it, and that face of the satellite just happened to be pointing at the camera when astronaut Tim Peake took pictures of it being deployed. So I literally got to see my name in space. That was a culmination of years of work I've done that started in grad projects. I got to be involved in almost every aspect of it: mechanical design, machining and assembly, FEA, thermal modeling, vacuum testing, systems engineering, boatloads of other testing, project management, electrical assembly, gas software development, mission operations, SDK orbital simulations. And you know what? I did all those things because they were fun. And objectively, it is so cool to work on a real project. Now, I'm the principal investigator for a $9 million NASA CubeSat called Sunset, and I was able to pull off this leadership role so early in my career specifically because of that experience I had that started in grad projects. So I hope that you take advantage of the opportunity that grad projects provides.
All right, great. And Nathan, would you like to follow that?
No, but I will.
So Nathan, he is one of our teaching fellows here for the Graduate Projects program, but he was just in Graduate Projects. So tell us a little bit about your background.
Sure. So I had kind of a weird progress through Graduate Projects. I took Graduate Projects 1, I think fall of 2021. And then instead of taking it in the spring semester, I took a semester off to do an internship, and then did it followed up in the spring, mixing up the dates. But basically I had a semester and a summer in between when I took Graduate Projects. So first time when I took it, it was working on the life support system project, and that was designing a life support system for the human landing system. It was more of a conceptual design. The scope was kind of reduced because we were still kind of getting out of COVID protocols, but got to work with Professor Nabedy and Stu Tozer at BioServe to actually do a full first pass design and a full life support system for the human landing system, working with NASA requirements and NASA ConOps. And we kind of worked with Northrop Grumman, but then that kind of got weird. So I was the systems engineer on that project. I had thought I knew what systems engineering was. I went through space habitat design, and they said they did a systems engineering education approach to it. Realized in the graduate projects how much I didn't really know about systems engineering, got to apply a lot of that. And then I did 2 internships in a row, both in systems engineering, realized there was so much more I didn't understand. And one really cool thing I got to do was apply that information on my second semester for graduate projects, which is, I think, super cool. You can take a lot of your personal experience and mold your own journey in graduate projects, working on something that is incredibly real and cool. The other thing, I guess, is I don't think a lot of other classes give you an opportunity to work in a situation that's as close as it's going to be in a professional world as an engineer, because you're given tasks and deadlines, but it's up to you to figure that out. And for the most part, your relationship with the instructor is more of a customer relationship than a student-teacher relationship. So I got a lot out of that. And also I got to work on a life support system. It's in the low bay. It's awesome. So I guess is that enough?
That's great.
Yeah.
Yeah. Okay. Yeah, you brought up a point that is very important, I think, and I think most students here can attest to that you get to work with a faculty member on something that they're interested in, that they're trying to bring to the world, and that you really can't get in a classroom. So it's a pretty cool experience. So with that, I'm going to bring ACES up first. They have 5 minutes to get through their slides. Just go through them as quickly as you can, and then there's time at the end. Anyone that has questions. No. Thank you.
Hello, everyone. I'm Galen, and I'm the lead simulation and controls engineer for ACES. We are not a CubeSat project, but a CubeSat attitude control system project. We're sponsored by Aerospace Corporation and LASP. Before we get started, basically, if you're someone who's, say, an ASN or really interested in spacecraft GNC, I think this is a really awesome project that gets into like a lot of good depth and a lot of those interesting algorithmic and design questions about real GNC systems. So yeah, what's the motivation for our project? I'm going to go over this really quickly. NASA released this survey on astronomy and astrophysics in 2020 with the idea of developing technology to answer some of these really big questions about our universe. And as part of this, there is a need or a desire for better technology in a few areas. And one of those is kind of distributed formation flying instruments with very fine pointing accuracy and pointing knowledge, specifically for, lower cost and smaller spacecraft like CubeSats.
Hi, everyone. I'm Julian. I'm the systems engineer on the project. Kind of like what Galen just said, we are not designing a CubeSat itself. We're designing something that's more plug and play on a CubeSat. So this module right here is about 5 centimeters by 10 by 10. And that you're just going to be plugging in on a 3U, 6U CubeSat, and it'll tell you your very fine pointing knowledge. So kind of the ConOps is being able to determine the attitude to about like 1/1000th of a degree. Just so you can get some very fine measurements with a radio or some sort of telescope.
Here's yeah, we have some pretty strict pointing requirements, like Julian mentioned. So basically, the idea of this project is to develop an attitude control system that meets these really strict pointing requirements for astrophysics measurements for things like CubeSat telescopes or similar missions. Again, we're a standalone ADCS module that's being developed to be integrated into these types of astrophysics CubeSats. And because of that, the whole system both has to be very accurate and also has to fit in these pretty small mass and volume constraints.
As far as organization goes, our team is pretty small, which makes it pretty nice if you want to be able to be very flexible in what you're doing. So most of the people on the team have been able to work on trade studies. For example, Galen has helped us on trade studies on star trackers because they've had, experience before. And that's all across the board. We've X'd out some people just because Galen's leaving next semester since he's graduating, and Hunter is also graduating next semester. So that's why we're here to kind of recruit you guys.
Yeah, here's this small kind of Gantt chart like overview of some progress that we're making and what's upcoming. We're about to give a Delta PDR tomorrow, actually. We have a hardware selection review and a model and some verification review later in the semester. And then starting next year, we're actually getting into working with a lot of hardware next year, meaning in the spring. We'll be working with a lot of hardware, ordering hardware at the end of this year, and then putting together a flat set next semester. So it's a exciting time to be on the project.
I guess Galen kind of just talked about this, but the spring plans, so hardware component testing, we're going to be ordering all our hardware about the Thanksgiving timeframe, hopefully getting that with our around March or February, integrating that to FlatSat, developing the flight software is currently being done, and then testing and simulation with Basilisk, which we'll kind of touch on a little bit later. And milestones for next semester are the FlatSat readiness review, where we meet with Aerospace and LASP, and we kind of show them what we've done, and then the CDR before we integrate into our actual final products.
Yeah, and here we just put together a list of some skills that we're looking for this project for next semester, as well as, I mean, I think this also matches pretty well with, you know, if you're interested in these kinds of courses and have this kind of experience, this project would probably be a good fit for you. But we are looking specifically for people with a lot of software development experience would be great. Basilisk is the simulation framework that we're using, and that is primarily in Python and either C or C++, depending on whether you're looking at dynamics components or flight software. And then we're also, like we mentioned, we're putting together a flat set next semester. So there's going to be a lot of like avionics and kind of test hardware development work to do there. So we're looking for people with a lot of electronics prototyping experience as well.
Okay, great. Thank you. All right, SwarmX, if you don't mind. I should mention that graduate projects can be taken sequentially and start in the spring and then end in the end of the fall semester, or you can take it in the fall and take a gap year and come back in the fall and complete it. So there's a lot of flexibility there, and a lot of the projects continue for multiple semesters. So, all right, I'm just going first.
Sweet. Hey everyone. So I'm Raj. This is Matt, and we work for SwarmX. So yes. So Dr. Pelo is our PI. He looks over the SwarmX project and the upcoming CubeSat projects as well. So yeah, we are a CubeSat team. We work on CubeSats. I work for the system engineering team. He's for the science and instrumentation part. We have our lead system engineer, Colton Brown. He's undergrad senior student, and we have Shibani as our project manager, who is in the engineering project, engineering management department as a grad student. So SwarmX stands for Space Weather Atmospheric Reconfigurable Multi-Scale Experiment. It's a CubeSat project funded by NSF, the National Science Foundation, and it is a CubeSat team that is distributed across the US, across 6 different universities, but it is spearheaded by CU Boulder itself. We have So we have Stanford University, University of Western Michigan, Oregon College of Engineering, Georgia Tech, and University of Southern Alabama helping us in this venture. And we'll talk about what each and every one of the teams look forward for the project. To Matt to talk about the objectives.
All right. So SwarmX has 3 main objectives. We have the science objectives, which I'll go over in the following slides. The engineering objectives, where we want to demonstrate CubeSat formation flying using propulsion and differential drag. And we also want to be able to communicate between the satellites using ultra-high frequency antennas. And then, of course, there are those like education objectives or something. I don't know. So what SwarmX intends to do is to study the coupling between the equatorial ionization anomaly and the equatorial thermospheric anomaly in low Earth orbit. It's important to understand these two features because they're primarily composed of atomic oxygen and oxygen ions. atomic oxygen degrades spacecraft material, and yeah, not great. And then the production of oxygen ions indicates, production of electrons, which leads to spacecraft charging, GPS scintillation, also not great stuff. So the primary science questions that SORMEX aims to answer have to do with the correlation between the neutral and plasma densities in these features, and looking at how persistent or not persistent they are over timescales. And doing this simply isn't possible using only one orbital spacecraft. So instead of one, we are using 3 CubeSats. And this animation shows what them in orbit would look like passing through the magnetic equator. So we plan to launch by 2025, and this is what's going to happen when we launch. And here's a diagram of the different configurations that these spacecrafts will be in throughout the duration of the mission. So during our guidance, navigation, and control operations, they'll be separated less than 3 kilometers apart. But during the the science operations, they'll be up to 1,300 kilometers apart. So this initial mission is only consisting of 3 CubeSats, which can take local scale measurements. But if this mission is successful and the results are favorable, then we could scale this up into a larger constellation to get regional scale measurements and eventually global.
Yeah, so that's our goal. That's what SOMEX is doing. Like Matt said, we are planning to launch by 2025. So right now we are focusing more on testing and hardware integration at CU Boulder. So as you can see, CU Boulder is responsible for a lot of the subsystems. Like obviously we have our project manager over here. Our PI is from CU Boulder. I'm also working in the AINT team. That's the assembly, integration, and testing team. We are starting to do a lot of testing and integrated testing on the CubeSat and see how that goes before our PIR, which is upcoming in the early next semester. PIR stands for preliminary pre-integration review. So we are hoping for that. And like I said, Georgia Tech is working on the propulsion module and the ADCS module. Orland College of Engineering works for the structures team. So we have a very vast demonstration of that. Right now, we are actively looking for someone who has experience in ADCS. Basically, we have a ZAC component. It's an ADCS module that we are trying to work upon, get some testing done on that. Someone in the communications who has good understanding of the electronics, so can get some testing done on that. AINT team is looking for someone who has good experience in the hardware side of it and can help us, with all the assembly and can devote some time in the lab to work on that. We recently got a news that SOMEX is also going to be setting up a ground station here at CU Boulder. So we definitely are looking for someone who is experienced in programming, C, C++, Python, and can really help us in that aspect of SOMEX. So yeah, if you are really interested to join SOMEX, if you want to start right now, you can mail any of these guys. They can help you with the recruitment part, and you can start as a volunteer, but then continue as a grad project course.
All right. Hey guys. Well, I'm Joey, the project manager for the series project, and this is Garrett, the systems engineer for the series project. Currently, we're the only 2 members out of graduate projects working on this, and we're also collaborating with about 10 or 11 undergraduate students for independent research. And we're working with Dr. Nabity and Dr. Nabity from the Bioastronautics Focus Group and Stuart Tozer from the BioServe Space Technologies Group. And we're working all together to investigate novel CO2 removal methods for ECLSS systems. So ECLSS stands for Environmental Control and Life Support Systems. And what we're doing is we're working with the Boeing ECLSS group out of Houston, Texas, to investigate specifically regenerable and minimizing consumable options for long duration trans-Martian space habitats. So what that means is currently the most state-of-the-art technology is using a lot of consumable systems and they throw it out after. So what we're trying to do is use a system that can be constantly recycled so we can keep it a closed loop and not waste a lot of mass going up with consumables for these long-term missions. So our project goal is to integrate onto a previous ECLIS research group's system called the HERD ARS test bed. And we're going to integrate onto there because they already have a system that can feed CO2 into a small vessel, which we can interface with. And we can test if our system can scrub the amount of CO2 needed per Boeing's requirements. So we're a brand new group this year. So all the other groups have been kind of building off of one another. So if you're interested in starting from the ground up, because we're starting literally at conceptual design, so and moving towards PDR hopefully by the end of this semester. So yeah, there's a lot of room for growth and really starting your own project here. Now, Gary, you want to chat about projects?
So basically, the deal is NASA wants to go to Mars, and how they're going to do it is something like this. This is sort of an artist's rendering of the spacecraft they might do it with. These are both Orion modules docked to it. And the idea is they're going to send about 4 astronauts there, probably for the duration of roughly 19 to 25 months. They don't really know, but the whole idea is 7 months there, 9 months back, roughly 3 months there, some bookend time in between. And so our deal is we need to make a system that can survive roughly 3 years with minimal maintenance, and be actually effective at removing carbon dioxide down to a roughly 1 millimeter of mercury level. So that's sort of our project goal. Currently, the state-of-the-art technology on the ISS can only get down to about 2 millimeters of mercury. The atmosphere normally is 760, and the actual amount of carbon dioxide normally down here is more like 0.3. Now, so this is kind of a high benchmark to get, over 3 times what is normally down here. But even on the ISS, it's even higher than that. And that can lead to some long-term problems like headaches and decreased cognitive function. And especially on a 3-year mission, when you're stuck in this spacecraft with no one else but these 4 astronauts, you kind of want to make sure you don't get headaches and you're not being confused. So that's kind of our deal. How do we remove 1.3 kilograms per person per day of carbon dioxide from that spacecraft?
And then so we were provided some specific requirements from Boeing, and these were derived from the system that's they currently helped work on the ISS, and that is what we're seeing here on the left, the carbon dioxide removal system. Pretty straightforward. Its name is CEDRA, and that's where we're deriving our performance requirements from. So, like you said, less than 1 millimeter mercury, partial pressure of CO2. I don't really want to repeat what we were talking about, but we're all about minimizing consumables, maximizing regeneratives, and also being durable without performance degradation for more than 3 years. So the way our team looks right now is because Garrett and I kind of started conceptual design very early on, we ended up taking the more leadership admin positions up at project manager and systems engineer. But we then kind of flowed that down to where the undergraduates are working, where they are separated out into mechanical fluids and data acquisition and control subsystems. But currently their roles kind of differ from how we're formatting those systems because we're still in conceptual design. So they largely were working on trade studies for different CO2 removal methods, which the ones we looked into were metal organic frameworks, ionic liquids, and biology-based approaches. And we actually just came to the conclusion and decision point of that trade study after a systems requirements review with Boeing. And we ended up deciding on ionic liquids, which we'll chat about in a bit. But yeah, that's kind of leading into what the deliverables are for this semester, which is honestly changing a lot right now because this is so research based. And as we're discovering these technologies, we're discovering even more novel approaches that need to be investigated on the component level rather than the system level. So right now we wanted to have our PDR and CDR in the same semester per Boeing's request, but that is slipping quite a bit, and which is okay because that was just kind of a rough outline. And once we chat with Boeing, we're okay with pushing it back and really extending this project so we get a good solution out of it. So hopefully we have PDR by the end of this semester, and then we'll move into CDR next semester. But yeah, so we actually already got to get some face-to-face time with the Boeing crew about 2 weeks ago. There's the 3 folks up front. They flew out here and they plan to be really involved with us, and they meet with us every week, and they also are coming to our reviews all the time. So it's really great because we get to really work with groups that hopefully we get to work with professionally more in the future. But to move on, we'll kind of talk about the work we've done to date for the training studies.
Pretty quick with this. Yeah.
So
No, this is that part's not necessary. This part is the one we want to talk about. Yeah, so right now this is sort of the result of our trade study. We chose ionic liquids, sort of based on a vote. Ionic liquids are effectively a salt, a organic salt that is some, really complex organic molecule with a hellish tongue twister name, that is really just a liquid salt with organic compounds. And what it does is it grabs carbon dioxide out of the atmosphere, bonds it weakly to it, and then you can heat it up and get it off. And that really highly selectively removes carbon dioxide from the atmosphere.
I just gotta
You just go.
cut it off now. I think we're done. Yeah.
So as we continue to make this design, we are really looking for help with rapid prototyping, which is our sort of next phase in the next semester. We'll go through most of the sort of design conceptual stuff this semester, but then next semester we'll really want to be doing some rapid prototyping, and we'll really need some help for that. So that's what you'd be getting into.
Thanks.
Hi, I'm Tycho. This is Blake, and we are here from the Maxwell team at the CubeSat project. And yeah, we want to tell you a little bit about it. So first, we're going to start with an overview of the mission we are investigating. And this is our acronym. As you can see, it is massive in stereotypical CubeSat fashion and is kind of a stretch. But it is a 6U CubeSat that was designed, built, and tested here. We are we're sponsored by the University Nanosatellite Program. They fund a bunch of these CubeSat programs all across the US. And our PI is Dr. Scott Palo. And we were scheduled for completion in 2023. That is not the case and has been pushed back. So we're hoping to get this launched and into orbit relatively soon. There's a cool little 3D diagram of it. So what are you doing this? Let's imagine you're working on like a spy satellite. That's kind of cool, right? And you take a picture and you need to downlink it back to Earth. Let's say it's a high definition picture. So your downlink process might like something like this, where it takes quite a bit of time to download the whole image. That's a problem if that image contains really important information that needs to get sent to Earth quickly. Another problem is that the communication band is getting very crowded, like a congested intersection. This is a visualization of that, and you can see it's kind of a mess. So our technologies aim to fix both those problems. A little CubeSat. And so we're doing that by doing high rate communications. Again, that is trying to fix this image problem. And then also with what it's called code division multiple access, CDMA right there, where you can hopefully kind of circumnavigate this clustered signal problem by doing cool stuff. If you want to learn more, come join our CubeSat. And yeah, here are some of our mission objectives. We have those communication objectives. We additionally are flying a chip scale atomic clock experiment that is through Dr. Axelrad's lab. So we are not doing the science on that, but we are basically housing that experiment for them.
Yeah, so basically the mission ConOps here, we're launching, deploying, doing our science and experiments, testing out the CSAC, the chip scale atomic clock. Then finally, we have this big antenna that we deploy, and that will also coincide with the end of the mission where we deorbit. So I can talk quickly about the hardware here. We have a custom core avionics, 2 radios, ADCS system with all those components listed, as well as the PLDC, which houses the CSAC and talks to the MMA T-Dagger, which is that deployable antenna. Here's a little image of the custom avionics that we were talking about earlier. We have an EPS system, CDH, ADCS, and all 3 of these systems were developing custom for the project. So right now, our semester goal is we have this big design review with the UMP folks, the Air Force Research Laboratory, here at the end of the semester. And then we're looking forward to a PIR in April. So those are kind of the big deadlines here, and just a graphical view of where we are in the project. So still like probably halfway through. We have lots of hardware and we're just trying to get this project wrapped up. So just in terms of the skills that we're looking for is systems. We're always looking for systems people, pretty much anyone. And then AI and T, that's kind of more hands-on test experience with the hardware. We're looking for CDH and PLDC people, so that's more of a software side of things, experience with C, and also just kind of a systems level understanding there. We need comms people, and then finally structures people as well. So yeah, structures is going to be more hardware focused, like I mentioned earlier. But yeah, we're just trying to get this project through the finish line. So just need some more hands to help get it over the line.
Two more for those keeping track, medics and Ralphie.
Yeah.
Medics is first.
All good to go. Awesome. All right. Well, hey, everybody. I'm Ben. I'm the project manager of Team Medics. This is Brett, the deputy project manager of Team Medics. And today we're going to give you an overview of what we're doing with our project right now and how you could be a part of it, or what comes after it, I suppose. Oh. Messed something up. Okay. Nope. Fixed it. We're good. All right. So, for those of you that don't know, our one of the courses offered through CU in grad school is the MISSE course, the Medicine in Space and Surface Environment course, where students will go out to the Mars Desert Research Station out in Utah and go through simulated medical emergencies and simulated EVAs in order to teach us more about how people living on Mars, far away from any doctors that can help them, would respond to some kind of emergency crisis scenario. Our goal as a team then is to help increase the fidelity of these simulations by building a medical bay out of the back of a mobile trailer that can be brought out to Utah and used as a sort of doctor's office for the astronauts during these simulated EVA emergencies. So our project has a couple levels to it. There's a conceptual design stage where we work to update the design of this trailer from last semester, where there was a very preliminary version made. And once that was completed, we are actually moving on to building the trailer itself so it can be brought out to Utah and used hopefully in the spring. Pictured there is the trailer, which lives outside on the west side of the building right now. We're currently working on painting it and installing power soon, which is very exciting. So part of this team, what it means to be on this team is kind of juggling back and forth between working on very conceptual things and then getting to work on a little bit more hands-on work. Here's a ConOps of what our, we call it the Mars Emergency Clinic, or the MEC. What the MEC would work like when it's finished. People are going through a simulated EVA out by the Mars Desert Research Station. Someone is injured in the simulated EVA and is brought inside our module where care scenarios can be run through to get a better understanding of how we should train astronauts and how the students' skills in what they've learned so far have paid off, ultimately to get a better understanding of what it means to practice medicine in a hostile environment like the surface of Mars. I'm going to pass it off to Brett then to talk about the org chart and some of the people we get to work with on this project.
Thanks, Ben. As Ben already mentioned, my name is Brett Bennett, and I am the Deputy Project Manager for Team Medics this term. As Ben just mentioned, this is our organizational chart, which conveys not just how the team is structured, but who we are working with as part of the delivery of this particular project. You'll notice our project advisors or advisor in this case is also our senior engineer. That would be Colonel Jim Voss. Our senior manager is Mr. Rick Heeb, and we also coordinate with the BioAstro and ADEM team, whose point of contact is Dr. Ali Anderson here in the department. You'll notice a financial component, a safety component, very much a systems engineering component, and we also have a technical director that oversees our separate subteams. This is just a little bit of technical data. This is our MPV budget across our subteams. We thought that this would be highly applicable for a technical audience as well as potential new team members. We have our CAD drawing that includes both the EPS system, which is roof mounted, our ECLIS system / HVAC system that is also roof mounted. And then you also get an idea of the layout of the structures, including a bulkhead in the back and the actual medical facility itself. This is a set of two-dimensional cross-sectional drawings, also depicting the interior of the trailer as it will look once it's finished. Of note here is several human factors considerations, the testing for which we also incorporate in this project. And we'd like to encourage you to join us. We're specifically looking for individuals with human factors testing experience, the ability to generate CAD drawings, as you've seen here in the presentation, and also to do plenty of systems engineering work as well. Any other comments?
Yeah. No, thank you, Brett. Also, as some of you may have noticed, we're almost finished with this exact project. So while we're not recruiting for people to finish the mech itself, we're hoping to have that done before December, fingers crossed. But in the next semester, in the semester that going forward, this team in general, as it won't always be medics, is the sort of human space flight team working with Colonel Voss in a lot of ways. And while the project next semester will certainly be something different from this, a lot of the general ways in which work is organized, what you can expect to be doing, a mix of conceptual and hands-on design, and a sort of focus on that human spaceflight is ultimately what the current medics team and in future semesters, whatever we become next, is focused on. And if that sounds interesting to any of you, come and join us.
Last team.
I guess we had a picture of the low fidelity mock-up in case anyone asked it. It looks way better than this now, but this is when we first built it with cardboard to get all the sizing stuff spaced out. So
Last presentation.
Oh, horse turn. Yeah, 6:45, right?
Oh, you got 5 minutes.
Alrighty. Hello, everybody. I am Alex Nelson. I'm the current chief engineer for Ralphie. This is Tristan Workman. He is actually in the class, so he can hopefully relate a little bit more to the grad projects class. But I took two semesters of it, so I know a little bit myself. We're representing Ralphie. It's one of the CubeSats here at CU. It stands for Radio and Laser Path Agnostic Communications Experiment. And don't look too hard at the acronym. You will hurt yourself. Our PI is Dr. Scott Palo, as well as the Maxwell and SwarmX team. Little introduction about kind of our motivations for our mission. So currently, one of the biggest issues that CubeSats face is that they have low bandwidth for their communications. And when you're doing a science mission like SwarmX and you're generating a lot of data, it's hard to get that information back down, which creates a big bottleneck. So technology demonstration we're going to be flying is for optical downlink, which has speeds of up to 1 gigabyte per second, as opposed to traditional UHF radio, which is about 20 kilobytes per second. So big increase on that. That's a really exciting technology we're going to fly. And also tied in with that is path agnostic communication. So a system which can determine which type of radio to use. So in our case, we're going to be flying X-band and the optical communication. And it has a FPGA on board, which can make decisions as to whether to use either of those communication channels based on message length and then also ground station availability. For an overview, we're using some heritage from some of the other CubeSats here at CU. So we're going to be using SwarmX's core systems like their EPS and CDH boards, and then we're going to be kind of basing it off a Maxwell structure. We did have to increase to 12U, so not an exact replica, but close. Also, some of the flight software developed by previous missions, including those two. For infrastructure, we're going to have a ground station here for UHF comms for telemetry, tracking, and commands. We'll have a commercial infrastructure for X-band experimental payload, and then an optical ground station here at CU as well for that laser transceiver. And then we also have a software-defined power controller, which we'll talk a little bit later with our payloads. For the schedule, we are over a year in development now, and we're about 3 months from flight selection review, which is a really big deal because that is deciding which ones of the projects in the University Nanosatellite program continues on towards an actual launch date, and we get more funding. So that's a big deal. Assuming that we do get selected for that, about 3 years from now, we launch. For our payloads, we first have the path agnostic communication system from Blue Cubed, a little bit like I talked about. We'll have the optical transceiver on, which has very few ground stations, but massive data rates. And then to counter that, we have the X-band transmitter, which has medium availability for ground stations, but only medium throughput. There's also plans to try to get network satellite radio on, which has high availability for communication, but very slow messages. Unfortunately, the company that was supporting CubeSats no longer is, so we have to look for a new one. And then lastly, we have Amplified Spaces software defined power controller, which is a plug and play power control board, which you can modulate the outputs for the voltages using only software commands. So this will be an off the shelf component that will reduce development time for CubeSats in the future. We will only be demonstrating the charge controller performance during flight conditions, but eventually we'll have 2 different power rails with anywhere from 5-volt to 20-volt outputs.
As Alex said, I'm Tristan. I'm the thermal lead for Ralphie, and I'll just break down a little bit the satellite bus architecture here. Ultimately, we're a communications experiment in orbit, and so the sort of crucial big ticket item here is the PAX, as Alex talked about a moment ago. We've also got a UHF antenna, as well as the bluefin antenna, which is how we're going to test out those communications protocols. We have the Exact, which communicates with the sun sensor, and the Novatel GPS for our ADC, and the board bus, where of course we have all of our CDH and other electronics, including the STPC located. You can move forward. So talking about future work, again, as Alex said just a moment ago, this is sort of a crucial semester for us because in a few months we get to step up to the plate for flight selection review. And again, if we successfully pass that gate, that means we actually do get to fly, we get to go to space. So we are recruiting hard right now to nail our in-person critical design review in December, and then be well prepared to talk to UNP in January for flight selection review. And then assuming we are funded afterwards, of course, we're going to step into testing and really refining and building this satellite. And so this is our organizational tree. There's about 24 of us, plus Ashutosh and Alex here. And of course, our PI is Dr. Pelo. We need systems engineers. Our mission design plans, the experiment, and ground system plans are underdeveloped because that is all coming after FSR, CDH, and EPS. If you like to design circuit boards or are familiar with flight software, we definitely want you. Comms, we're working on licensing for our radio usage. That's a huge pain in the ass. Again, if you have any experience there, that would be awesome. And then structures, we really need people who are familiar with finite element modeling. So if that's you, please contact us. I think we have our email on the next slide. Hit us up. Yes, we're Ralphie. And that's all, folks.
Good. Thank you very much. Thank you all of my enrolled students for being here tonight after last night's mid-semester presentations. My email, for those of you that would like to, you can email me there, which is a long one, aesgraduateprojects@colorado.edu, or my last name, koehler@colorado.edu. If you also have questions about the programmatics of graduate projects. Do you have any questions, anybody? Otherwise, we can let you take as many cookies home as you'd like and come up to the students and ask them some one-on-one questions. Any questions? Well, thank you for being here. Thank you for coming, and please take every cookie that's here. I appreciate it.